Alrighty, today we are going to be talking about the cardiac cycle. We are going to be talking about pressure volume loops, afterload, preload. We're going to talk about the baroreceptor reflex and how that affects heart contractility and how it affects blood pressure. We're also going to talk about capillaries and fluid exchange, and we're going to be talking about all of the different forces that drive fluid in or out of the capillary bed. And then we're going to talk about edema, because edema is very much associated with the capillaries. And so, yeah, first thing we're going to start with is pressure volume loops. So, with blood pressure, it is something that is constantly varying depending on heart contractility, depending on if you're exercising, if you're having an allergic reaction. There could be all sorts of things that are affecting your blood pressure. So something that we see very common is what we call a blood pressure volume loop. And so I'm going to draw a couple things here. This is going to be pressure. That didn't work very well. And this is going to be the same thing, pressure and time over here. And so these are going to be two comparative little loops that I'm going to talk about. And we're going to label a few things. First thing we're going to label here is M, and that stands for the mitral valve closing. Here is AO, which means the aortic valve is opening. Right here is when the aortic valve is closing. And then here is when the ventricular filling begins. And so I feel like this is a pretty straightforward visualization of what's happening. The one I'm going to draw over here on the right is a little more confusing. But obviously, when the mitral valve closes, there's going to be an increase in left ventricular pressure because now you have a chamber that's full of blood and there's no way to exit. And so the pressure is going to increase. Now, it's only going to increase until the aortic valve opens, which is right here. And then as the aortic valve opens, obviously blood pressure is going to begin to blood's going to rush into the aorta. The aortic valve closes. So yeah, then we're going to have this change in pressure as those valves open and close. And then it's going to decrease, obviously, as blood rushes out of the ventricle through the aortic valve into the aorta, not through the rest of the body. And then the left ventricle, as it begins to fill, that's when we're going to see this gradual increase in pressure as the ventricle fills with blood. Now, something you're going to see a lot more common that is associated with this is a pressure volume loop. It's going to look something like this. Looks really bad. Do it like this. And I'm going to start labeling a few things on here. Where should I begin? First thing we'll label is kind of the same letters we started with on the other side. So M, this is when the mitral valve closes. This is when the aortic valve closes. Then we have the ventricles filling with blood. Then over here we have the aortic valve opening. This distance right here is called your stroke volume. And then we're going to have this side here. We'll label this D. Or I guess we could even do it like this. It's a little too thick. Do it like that, D. And then we'll do A. And then we'll do B. And then we'll do C. Okay, so now we'll label a few things. So this side right here, D, was what we call isovolumic relaxation. And this is when the heart is not contracting, so it's in diastole, and there is no change in volume. I'm going to move it so it makes a lot more sense when I write it. So A is diastolic filling. So this is when the heart is not contracting, so you only see a slight increase in pressure because the heart is obviously relaxed, but there is blood being forced into the heart, so it is filling up with, it is being filled up with blood. And so that's kind of how you can see this slight increase in volume down there. And then B, we have isovolumic contraction. Which I feel like is pretty self-explanatory. And then C is ejection. That is when blood is being pushed out of the heart. And yeah, so that's essentially what the blood volume loops look like. Let me see if I can think of any other things that I need to probably mention for the purposes of this video. Oh yeah, I forgot about this guy. So usually from a point like right here, there's a line that we use to draw through like that. And this line tells us a lot about contraction and volume relationships. So we'll call this the ESPVR. And this stands for end systolic pressure volume relationship. And then usually what we have is a little line that descends like this. And this is what we call EDPVR. And EDPVR stands for end diastolic pressure volume relationship. So the ESPVR is a pressure volume relationship that is represented at maximal contraction of cardiac fibers, and then EDPVR is a pressure volume relationship that is represented with at maximum ventricular relaxation. So both of these areas represent important characteristics of heart function, and ESPVR is what is commonly referred to as inotropy. And this is a very important term, which we're going to talk about a little bit more. So inotropy is the contractility of the heart. I talked about it a little bit in the last video, but it is the force of contraction that the heart muscle generates as it contracts. And it is a function of calcium influx. So as more calcium enters the cytoplasm of heart cells, there is greater movement of tropomyosin off of the actin myocytes, actin binding sites, which allow more actin heads to bind, which increases the overall number of myosin heads that can bind and cause a contraction. And so understanding these changes of inotropy are very important to understand heart function, because the heart can not modify its strength by recruiting more fibers or more active units. So basically all the heart cells are recruited at the same time, but not all the myosin heads need to engage. And so that's why, depending on the amount of calcium level that is in the heart, determines how many myosin heads will actually be able to bind. And so so what we're going to do here is draw a second line. That looks like this. It's kind of hard to see, but those are those little red and green dotted lines. And so what we're going to see here is when you increase inotropy, it changes how this diagram looks. And so I'm going to draw kind of what that looks like here. And so what that's going to represent is the change in pressure. So let's figure out a good way to describe this here. Basically, as the heart is able to contract more, it's able to push more blood out of the heart, which means down here, you're going to be starting with a lower amount of blood in the heart, which is also going to increase the stroke volume, right? You're moving it all the way back to here. So this difference now compared to this original distance is going to be a lot higher than it was before, which means the amount per beat that the heart is pushing out of the heart increases as it goes into the aorta. Now, if we have a decrease in stroke volume, it's going to fall along this line right here. And what we're going to see is something that looks like this. Increase just slightly above the control line. Like this. That's obviously not a completely perfectly medically accurate drawing. But what we're going to see now is this new stroke volume is going to shorten as inotropy decreases. So as we have less contractility of the heart, the amount of blood that the heart is able to push out per beat decreases because the inotropy decreases. And so that's why down here with volume, obviously this would be less volume. And so when we have a steeper line, that means that our preload, or the amount of blood that's getting moved throughout the heart, is going to decrease, and then the reverse, obviously, with a shallower line here, as you can see in between those. And then this is the control line. So between that angle matters a lot. And so the way this is mathematically often measured is a change of volume over a change in pressure, and that is what we call compliance. And compliance is the reverse of elastance. So it's like basically how firm the heart is, and then the change in pressure over change in volume is elastance. And the amount of stretch that the heart is able to give when it is in that relaxation phase, and isovolumic relaxation is how much elastance we have. So right here, we're going to start talking a little bit more about this. Talk about this area right here. Go back on that. So this line, this area, is what we call afterload. And so afterload is essentially the pressure that the ventricle must work against as blood is being ejected from the heart during contraction. So think about like if you were trying to push on a door while there was water against the other side of the door. If there's a ton of water, you're going to have to push really hard. And so afterload is that pressure required to eject more blood from the heart against that mitral valve, if that makes sense. Or excuse me, against the aortic semilunar valve. And afterload is affected most by arterial elastance. So if the aorta isn't very flexible, then the amount of pressure is obviously going to increase and the heart is going to have to work harder to eject blood from the heart. So what we're going to see is if we change afterload, what we're going to see now is a difference. Instead of moving left to right, what we're going to see is a totally different change so like right here, remember this black is our control line. So if we have an increase in afterload, so if the amount of pressure required to eject the blood from the heart increases, we're going to see something like this. So we have an increased afterload. We're going to have a shortened distance from the control. It's going to be a lot taller. And so there's going to be less volume here being able to be ejected. And you're kind of going to have this wider peak, this wider increase in pressure, obviously, because pressure's on this side. So we're going to need more pressure to push blood out. Now, if we have a decrease in afterload, so blue is increase in afterload. That's what it'll look like. But if we have a decrease in afterload, we'll get purple. What we're going to have is a slight deviation this direction. And so there's going to be So less volume in the heart. Oops. It'll look something like this. It's going to follow that same line. We're going to have less pressure because there's not as much pressure required to eject blood from the heart. It's going to look something like that. And so that is going to be a decrease in afterload. Okay, so now we'll talk about preload. So I'm going to draw another graph here. Pressure, volume. We'll have our control. Those are control here. I'll give you an example of what decreased preload looks like. So this is decreased preload, and then this is going to be increased preload. And so preload can best be thought of as the amount of stretch in the cardiac sarcomeres before they contract. So because as the heart fills up with blood, the amount of distance, I guess, or the amount of stretch that the cardiac, like kind of like a balloon, the amount it's able to fill up during diastole, because they're being passively filled up, they're not necessarily like purposely relaxing or contracting. That relaxing phase is stretching out the heart muscles. And so anyway, so if you decrease preload, that means you're decreasing the amount of blood that it is able to fill up the left ventricle as it is relaxing. And if you decrease the amount of preload that's able to fill up with the amount of available blood, that means when it ejects blood, there's going to be less blood leaving. Or if you increase preload, now you have a bunch of blood in there, and every time the heart contracts, you're going to be expelling a higher volume of blood. Alrighty. Okay, so obviously, as we know, capillaries are the smallest blood vessels that we have. So we're going to pretend that this is the capillary bed exchange between an arteriole and a venule. Now, every time the heart contracts, it's going to administer some type of force to the arteries. And this is summarized in a math equation called MAP equals CO times PR, which means the mean arterial pressure, so the average amount of pressure that's exerted on the arterioles, is equivalent to the cardiac output times the peripheral resistance. And so if you have a larger diameter vein, there's going to be less peripheral resistance. If you have a smaller diameter vein, there's going to be much higher peripheral resistance. So you can kind of figure out what that means. Pretty simple. Now, these capillaries are very fragile, and so each capillary has something called a capillary sphincter, and these contract and basically can help protect the capillaries from bursting. Let's say, so these are some cells that are just right outside the capillary. These could be skin cells like endothelium or whatever. Anyway, I'm going to go back to my other notes real quick and review what I learned. So essentially what's going on here, what I was drawing there, I'll just kind of use this to explain what's going on. So the capillaries are filled with fluid and blood and nutrients and all sorts of things. And the hemostatic pressure of inside the capillaries is this number right here, 30 millimeters of mercury. And what this wants to do is push water from the capillaries outside into the extracellular space. So we have a couple different forces that want to push things out. So we have something called the hemostatic pressure, and then we have something called ICOP. And ICOP stands for interstitial colloid osmotic pressure. And again, that also wants to push water out at about 8 millimeters of mercury. However, you can imagine that if that was only the case, if there's nothing pushing water back in, we would just have swelling because there would be lots of water in the extracellular space, and that would lead to something called edema. Now what we have is all sorts of things that are present in the blood. We have things like sodium, potassium, magnesium, calcium, amino acids, and these are constantly moving in and out of the cell, but they don't take water with them. And then what we have is something called albumin. And albumin is a large protein, and albumin really wants to go into the blood. And that pressure that it pulls albumin into the blood is called BCOP. It's called blood colloid osmotic pressure. And so what we see between all of this movement in and out is we have an average at the arterial side of 13 millimeters of mercury that is pushing out and 7 in. And so there's this constant exchange of essentially of fluid pressure. Now here what we have is our lymph vessels. And the lymph vessel's job is to return any excess water that is outside the intercellular space or in that extracellular fluid and bring it back up so that you can get all of the venous return that you need, because unfortunately blood return through the vessels is not perfect, and so there's always going to be a little bit of blood and fluid and things left behind. But thanks to our lymph vessels, they bring that back and allow it to continue to be filtered and circulated throughout the body. And so on the venule side, we have an HP of 10, a BCOP of 28, an ICOP of 3, and an IFP of 8. And so anyway, there's just that constant change of fluid going in and out because of these capillary beds. One other important thing to note is that when O2 delivery is decreased, it's going to increase lactic acid, increase CO2, and increase potassium. And so what happens is we see in a decrease in extracellular fluid. And so that's kind of one of those things that's related to dehydration is, actually, I don't even know if that's true at all, what I just said. Oh, man. Hydrostatic, call it osmotic pressure, blah, blah, blah. Okay. I'll give now an example of edema. So what happens with edema is let's say you are allergic to let's say you're allergic to latex, and the latex causes a histamine release from your body that increases the amount of proteins that are present. So you get these antibodies, they react to the allergen like latex, and releases these little proteins, and these little proteins change they essentially change the concentration of intra to extracellular fluid. And so what that's going to do is, because now there's these little proteins, it's going to increase the amount of water that wants to leave. And what happens is this is much more than the lymph vessels can handle. And what that's going to cause is an increase in extracellular fluid that is more than normal. And that's how you're going to get swelling. So yeah, the last thing I forgot to talk about was something we call baroreceptors. And so baroreceptors are in the arterial wall right here, and they're also in the carotid artery. And what baroreceptors do is they tell the brain whether or not the arteries are stretching as usual, like normally, or if they are stretching less than normal. And essentially what that does is tell the brain whether they need to increase or decrease blood pressure. Yes, okay. So, brain cells die only after 4 or 5 minutes without action. So the baroreceptor plays a key role in short-term regulation of blood pressure, and it essentially what it does is they reside in the arch right here. They reside in the arch of the aorta, and then they in the carotid sinus. Yeah. And then they also reside in the carotid sinus. So let's say this is the carotid sinus, these little nerve innervations. And essentially what they do is they stretch whenever they stretch, it is proportional to blood pressure. And so it tells the brain the blood pressure that exists in the aorta or in the carotid arteries, and it responds by increasing or decreasing cardiac output. The brain does. So it sends signals back to the effector organ, like the heart, which is the heart, and tells it to increase or decrease cardiac output depending on the current state of blood pressure.